Welcome to Chapter 14 on water pollution, and welcome to the end of the year. We're getting close here, with only 4 chapters including this one. So let's get started. Okay, a few bits of information you need to know. Pollution is considered to be anything physical, chemical, or biological that changes the quality of the water that adversely affects living organisms, so the environment, other wild creatures, and humans as well. This includes contamination of streams, rivers, lakes, oceans, and groundwater, and anything that negatively affects organisms or humans. Two very important terminologies you need to know are point source and non-point source. Point source is from a distinct pipe, whereas non-point source is basically from a large area, if you will. And so those are very important terms. Flowing water means to be moving, and usually pollution is diluted by that movement and the change in water, so it's less important, while standing water is usually more damaged by water or by the pollution because it's standing or sitting in the lake and accumulating. So things like lakes and ponds are much more likely to have severe damage due to pollution, whereas rivers and streams, that'll get washed away and it won't be a problem. Okay, so is this point or non-point? Right there, that little pipe, that would be point. You're right, hopefully. And then this, all these cows on the field, that would be considered non-point. Okay, so human wastewater is a very important issue. Actually, wastewater of any kind from animals and humans is always an issue. Many cultures, many countries still wash and bathe and drink out of rivers. And so then water, wastewater, and human wastewater and fecal material become a much greater issue than they usually are here in the United States. When we're talking about wastewater, we're concerned about three things. The oxygen demand, which is the amount of oxygen required by bacteria to decompose the material that's being introduced. The nutrient release of this material, any biological material when it's broken down is going to become nutrients, nitrate, phosphate, potassium, etc. And those in excess in a body of water can lead to eutrophication. And we've talked about eutrophication in class, and we'll continue to talk about it because it's a very important concept. And then, of course, these causing organisms that can come in wastewater, disease, parasites, all that kind of stuff. So we'll go over that as well a little later on. When we talk about rivers and lakes, we need to talk about biochemical oxygen demand. You will hear me refer to it sometimes as biological oxygen demand. Either terminology is accepted, so either one is fine. BOD, or biological oxygen demand, is the amount of oxygen required from the water for a period of time at a specific temperature by organisms. So as there's more organic material entering a river, the microbes that do the decomposition have to use a greater amount of oxygen to do cellular respiration to do that decomposition. So they're going to, the BOD increases, which means they're going to decrease the DO, the dissolved oxygen level, the amount of oxygen in the water. It can get to a point where it creates an anoxic or hypoxic condition, which means there's little or no oxygen in the water, and that can lead to organism death. So lower BOD values indicate the water is less polluted because there's not a lot of stuff being decomposed, while a higher BOD value would indicate more pollution by wastewater or fecal material or biologic material in the area. Okay, this diagram shows what we call an oxygen sag curve. So the oxygen level, the dissolved oxygen level in the river is really high until an event occurs. And then that starts to taper off because your BOD level, which was very nice, healthy, and low, skyrockets very quickly because all these microbes are going to need to decompose all this material. So that is high, so your dissolved oxygen drops down very low. A lot of animals cannot handle this kind of low area, so you're not going to find fish here because they just can't survive. So you're going to have an area of the river that has very little fish. So it's kind of sick here. Once it's decomposed and moving in the river and getting diluted, the BOD will start to come back down and the dissolved oxygen level would go back up and you get back to a healthy river. So this is what's happening when you have wastewater entering a river. This can also be any kind of biological material entering the water, anything that needs to be decomposed entering the water. So effluent from a wastewater treatment plant or runoff from a farm with fecal material and stuff in it, anything like that can lead to this situation. And this is again called an oxygen sag curve. The oxygen sags. Okay. Nutrient release. Nutrient release is very important. The nutrients can come from a variety of sources, wastewater being one of them. It can also come from fertilizers in our agricultural area that contain nitrate and phosphates. Years ago, and still in some countries, soaps and detergents contain phosphorus. Phosphorus actually made your clothing much cleaner or whiter looking. And they took that out in the 60s, I believe it was. They banned it in the soaps in the U.S. because we realized that all that phosphorus ending up in our waterways and in our effluent water coming out of our houses was causing eutrophication. Eutrophication is basically a sick lake or a really old lake. Lakes will become eutrophic through a long period of time. It's a natural progression of lakes as lakes get older, but most of the eutrophication we see here is cultural eutrophication, which means we caused it. So either by the introduction of nutrients such as fertilizers or phosphate from detergents, or even wastewater that once decomposed by the microbes becomes base nutrients, will lead to eutrophication. The process of eutrophication is something you need to understand. The excess nutrients cause an algal bloom. The algae use it to reproduce and grow, and pretty soon your lake is green. Then they block sunlight, which causes a lot of your plants around the edge of your lakes and stuff to die out because they can't get enough light. And also often the algae will die themselves. So now all of a sudden you have dead material in the bottom of the lake that needs to be decomposed. So the microbes start decomposing. Again, they're using up a lot of oxygen. So the dissolved oxygen level in your lake drops. This causes anoxic or hypoxic conditions. Again, little or no oxygen in the lake or pond. And that will cause a fish kill. The fish can't deal with the low oxygen. They have nowhere else to go, and they die. Eutrophication is considered a positive feedback because it continues to happen. The decomposing bacterium or algae in plants give off more nutrients to the water, which causes the next algae bloom, and it just keeps going and going and going. There are a few ways you can fix eutrophication. You can add alum, A-L-U-M. It's a chemical to lakes that are eutrophic. It binds up the nutrients chemically, so they can't cycle and they can't be used by algae and other plants in the water. So you can do that. Or in a eutrophic lake, the bottom has that mucky stuff. It's decomposing stuff. You can also dredge that up or suck that up and remove that, because that's a lot of those nutrients that are cycling. You need to get the nutrients out. So you either have to tie them up chemically or you have to pump them out. Another thing we do a lot of times in eutrophic lakes to deal with the fish kill part is we aerate them. We introduce air in a variety of ways. The most common way is a fountain. By putting a fountain in, water that moves has more oxygen in it. So by creating movement by the fountains throwing up water and all, that will aerate your lake more and it will avoid the fish kill. Your lake's still eutrophic, but it keeps enough oxygen in the lake that you aren't going to lose your fish and have little fishies floating. Okay, moving on. Disease-causing organisms. Fecal material carries disease. It's how we shed it and stuff like that, and parasites. So we need to be very concerned. Fecal coliform bacteria is an indicator species. It's used to identify if there's human waste or any kind of waste from an organism in the water. So fecal coliform bacteria is an indicator. Fecal coliform bacteria itself is not dangerous or harmful to humans. So you can come into fecal contact with it and it's not going to hurt you. It just happens to be an easy indicator. So instead of having to test water for numerous fecal caused diseases, we can just test for this, and then we know the water's been contaminated and therefore may carry disease or parasites related to that. So some of the common waterborne disease are cholera, typhoid fever, the stomach flu, diarrhea, and hepatitis can all be carried in there. Cryptosporidium is a bacteria that's a parasite or makes you have a tummy ache and stuff. And Giardia is another parasite that's quite wicked, that gives you, it's a little guy that hangs out in your intestines, gives you diarrhea. Here in the United States, not a big concern. You're going to feel sick a little bit, go to the doctor, you'll be okay. But in third world and or less developed countries, it's a much bigger deal. Okay, so I'm going to cut this off here for our video 1, and then I will start video 2 and cover wastewater treatment. Actually, that's kind of crazy. Okay, never mind. We're going to continue. Sorry. Okay, so let's get through how we deal with wastewater. We talked about this a little bit in class. With houses, we have basically 2 fields or 2 possible choices, and they would be septic systems. A septic system is a large container that your wastewater from your house goes out into. The solids sink and settle in the bottom while the liquid is brought out into a leach field, and the water basically drips or leaches into the ground there. And this is all underground, kind of out of sight. Eventually, usually you have to have your septic tank pumped to remove the solids, but it's a very easy way. You usually find septic systems in houses that are very rural or are quite old and were built before the sewer system was in the area. Okay, the other thing is a wastewater treatment plant. The water heads out of your house into the sewer system. The sewer system takes it to the wastewater treatment plant. It's very important that you know the different parts of a wastewater treatment plant. So let's go through those. Okay, so here we go. So it's coming through, and the first thing that happens is it goes through a screen, a bar screen, a screen of some kind, basically to filter out large chunks. Debris, twigs, leaves, rags, Disney plushes, whatever it is. So it comes in here, and that's primarily to remove that material so that it doesn't damage any of the rest of the process. Okay, then it goes into primary treatment. Primary treatment is a settling tank. It just sits here and it settles. So it's very still. All your solids settle in the bottom and are collected as sludge. And then what's left is basically water with a few very tiny bits of material in it. That water goes over to the next tank. This is the aeration tank. There's air being pumped in here to allow for decomposition. So microbes are decomposing whatever material is left in the water, and of course they need oxygen for cellular respiration, so we pump in enough oxygen so that they can do a great job, and they're not going to stop doing their job because they run out of oxygen. So this is an aeration tank, and it's being bubbled in. There's also a catch here, again, for any sediment that settles out even in this stage, because we want to get as much solids out of that as possible. Next part of secondary treatment is some kind of disinfection. Usually this is chlorine. It can also be ozone or UV light. And that basically is going to take care of your disease and parasites. Everything up until now is to remove the solids. But now we can still have disease, potentially, or parasites in our water. So we need to disinfect it. So usually it's chlorine. Newer facilities might use ozone or ultraviolet light. And then it's usually either dumped in the ocean, interjected into underground, spread on a field, something like that. Some facilities have a tertiary component, and that's another round of disinfection, usually like UV light, that helps again kill all the parasites and the disease. And then that water often will go back to the community as what we call non-potable or gray water, and used for landscape is usually what it's used for. The sludge that's retrieved is either then taken to a landfill, burned, or used as a fertilizer on a field. Never a human food field though, so it's not on your vegetables or anything. Or it can be made into Milorganite, and Milorganite is a fertilizer that you can buy that's made actually out of human waste. It's a nice pelleted material, but it is actually made out of human waste. So let's see, we're going to just go ahead and do animal waste really quick because there's only one slide, and then I will cut this short and we'll continue on. Okay, so animal waste is always a concern. In a lot of places where there's a large amount of animals, like here where we have these large feedlots, this is a manure lagoon. It should be a lined basically pond, and this is all fecal material and water. And the idea is that the water will evaporate off, leaving the fecal material, and then that can be taken and used as fertilizer on fields and stuff. Sometimes these leak. Sometimes they have cracks in the liner. Sometimes they don't really put a liner in them. And all this can leach into our groundwater and stuff, which is pretty nasty. If any of this were to get out into a river or in a stream, it would cause either an oxygen sag curve or it would cause eutrophication. So we want to try to control that as much as possible. And we're going to cut this off here. Thank you for listening. Have a great evening, guys.